Hi, and welcome back. Today we're going to continue talking about singular value decomposition. That's actually over the next couple of lectures. Um, and the goal of today is to try to understand what the singular value decomposition does geometrically, as well as a couple of first basic properties and consequences of the existence of the singular value decomposition. Okay, so all I've done here is I've just rewritten the mnemonic for remembering how the singular value decomposition works. You take any m by n matrix A, and you can write it as U sigma V transpose, where U is m by m. The first R singular, those are the left singular vectors, the U's, right? The first R are sort of the ones that matter, and then the rest of them give you an orthonormal basis of Rm. So U is an orthonormal matrix. You have R non, or you have R positive real singular values going along the diagonal of of the sigma, and then you have a bunch of zeros at the end, and that's an m by n matrix, the same as A. And then V transpose, which I've written down here, uh, those are the right singular vectors. Since you're taking the transpose, they're the rows of V transpose. That's an n by n matrix, and again, sort of like the first R are sort of the ones that matter, and then the remaining n minus R ones are the ones um, that matter a little bit less. Okay, I should have said the rank here of A is R. Okay, and there is a reason why you might sometimes want to know the full singular value decomposition rather than the reduced one, right? So we said yesterday that if you just take the first R left singular vectors, so now this one is m by R, and you just remember, you can take this diagonal matrix, this one is R by R, and you remember just the first R right singular vectors, so this one is R by N, then this is also equal to A. This is the reduced SVD. But we'll see that it is genuinely useful sometimes to keep in mind the entire matrix U and the entire matrix V transpose, uh, because you'll be able to think more clearly about what the singular value decomposition actually does. Okay. So first, we're going to just look at some consequences of the SVD. Again, the SVD has lots and lots of applications and consequences, but here's one application, is that you can write any matrix as a sum of rank 1 matrices in a really nice way. So this is called rank 1 decomposition. Okay, and rank 1 matrices are very simple, right? But to say that you can write a matrix as a sum of rank 1 matrices is like very trivial, right? You take any matrix you want. There's lots of ways to write it as a sum of rank 1 matrices. There are three very natural ways that are sort of obvious. You could just write it as the sum of its rows, like this, right? So each of these is a rank 1. There's only one pivot. You could write it as the sum of its columns, right? I'm being a little bit loose by sum of its columns, right? What I mean is just break it up into three pieces based on its columns. You could even just write it as, you can just take each entry individually, right? There's 6 terms here. Let me not write all of them. So to say that you can write a matrix as a sum, as a linear combination of rank 1 matrices is a totally trivial statement. But the SVD provides a really, really useful one, right? These are natural enough, but there's a very, very useful one that comes from the SVD, and we'll even see the applications of why it's a useful one. Here's the theorem. So let A in R m by n be a matrix of rank R with reduced SVD as on the previous slide, or for you in the notes above. Then A is equal to sigma 1 U1 V1 transpose plus dot 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 plus sigma R UR VR transpose. And each sigma I UI VI transpose is a rank 1 matrix. So this is a rank 1 decomposition of A. And it's like a really nice intrinsic one. One way to see that is that the number of terms you have is R and the rank of the matrix is R. Right? So if you took any of these like sort of trivial rank 1 decompositions, like no matter what, if I take any 2x3 matrix and I do it by the rows, I'll always get it's the sum of two things, right? If I write it in some terms of its columns, it's the sum of three things. If I write it in terms of entries, it's the sum of six things. So the number of terms here isn't telling you anything about the matrix. If you take the SVD one thing that somehow it's capturing is the rank of the matrix, because that's the number of terms you'll have in this this rank 1 decomposition. Okay, and the proof actually is not so bad. The point is that say you write A in terms of its reduced SVD, then this is U and then this diagonal matrix like this, V transpose. And I can break up this diagonal matrix as a sum of very simple matrices. Right, where I just keep one of the sigmas along the diagonal. Okay, and then what you notice is if you take a look at this first one, right, consider this product. If you think about what's happening in this multiplication, there's only one non-zero entry in the whole matrix. And so when you perform this matrix multiplication, only the first column matters at all. If you change any of the rest, only the first row matters at all in the V transpose matrix. If you change any of the other rows, it doesn't change your product at all. So you might as well take them to be 0. It's not going to affect your answer. Same thing on the left. If you think about what happens multiplying by the matrix U, it doesn't matter at all what the rest of the columns are, because the only entry you're going to multiply it by this matrix anyway. The only entry that matters that's non-zero is the top left entry, so only the first column of this matrix matters, and only the first row of this matrix matters. But now, if you were to do out this product, try a small example on your own. This is the same thing as if I just replace this with sigma 1, just replace this matrix with V1 transpose, and just replace this matrix with U1. These would be equal. The products are equal, even though I've changed all the matrices. Okay. The sizes are also okay, right? This one is R by R. This one was R by N. This one was M by R. I've just changed it to M by 1, 1 by 1, and 1 by N. Right, so the size is actually okay. This thing will end up being 1 by N. Okay, and then why is this thing rank 1? You can think of it as what is the column space of this matrix thought of as the range of the linear transformation. And the point is that this last linear transformation has a one-dimensional range, a one-dimensional column space. So if that's the last thing you do, right, you do one linear map and then you do another one, and the second one only has a one-dimensional range, it means the composition can only have a one-dimensional range as well. And these things will be non-zero, so you'll have exactly a one-dimensional range, which means that it's a rank 1 matrix. Okay, so this is a little bit of a hand-wavy proof. There's no proof given in the notes, so I thought I would just explain of why you get this rank 1 decomposition as a sum of R rank 1 matrices. Okay, so this turns out this is one useful way to decompose your matrix as a sum of matrices that we'll see will become useful. There's another immediate application or consequence called the polar decomposition. This one only works for square matrices. So if A is a square matrix, then you take the SVD like this. Okay, this is the full SVD, so all of these are n by n. And what you can do is you can just insert a little V transpose V sigma V transpose in here, right? So this is just the identity matrix because V is orthonormal. It's a square orthonormal matrix. Its inverse is its transpose. So this is UV transpose times V sigma V transpose. So this, again, these are all square matrices. And now the point is that if you multiply together you multiply together an orthonormal matrix and the transpose of an orthonormal matrix, you will get an orthogonal matrix. So this one is orthogonal. You can check that. It requires a little bit of proof. And this one, because sigma is a diagonal matrix with all non-negative entries, you can take their square roots and split them up over the V and the V transpose. So this is just sort of shorthand, but you can kind of write it like this. And it turns out that these two matrices that I've written down are transposes of one another, which shows that this matrix is positive semi-definite because you can write it as something times something transpose. Again, I've been a little bit loose here. This is just a hand-wavy explanation. Therefore, since SVD works for any matrix, this shows that every square matrix you can write as an orthogonal thing times a positive semi-definite thing, which is, I think, very non-obvious, right? So every square matrix is the product of an orthogonal one and a positive semi-definite one. So this is like a matrix factorization. And the point is that a general matrix can be complicated and confusing, but positive semi-definite matrices are super nice and orthogonal matrices are super nice. So it's sort of like you're decomposing the linear transformation into two very nice pieces that you can understand better. So there are also uses for polar decomposition in terms of understanding what a matrix does as a linear transformation. Okay, so these are two immediate consequences of singular value decomposition that are both genuinely useful in terms of understanding what a matrix is doing. And for the rank 1 decomposition, we'll see that it has some applications to image compression in a little bit. Okay, but now I want to start talking about the geometry of SVD. In other words, what it really does, right? So the idea is one that I even talked about when the very start of last lecture, when I said what the SVD was kind of like diagonalization. We said that diagonalization is like a change of basis, then a nice action, then a change of basis back, right? And we choose a really nice basis. We choose a basis of eigenvectors of A. Well, we can take the idea that writing A as xd x inverse is like writing it as three separate linear transformations that altogether give you A. Well, in the SVD, we write A as U sigma V transpose. It's like we're writing it as three different linear transformations that when you compose them, you get A. And we can understand each part to have some idea of what A does overall. So that's the perspective that we're going to take, right? So let A be an m by n matrix. We don't need it to be square. And write A equals U sigma V transpose, the SVD of A, the full SVD, right? We should be always careful if we're talking about the reduced SVD or the full SVD when we're doing things in the abstract like this. The point is that every matrix of m size m by n can be thought of as a linear transformation from Rn to Rm that sends x to Ax. This is what you've been learning since 308. But again, Ax is equal to U sigma V transpose X. So you can think of what A does as first you do V transpose, then you do sigma, then you do U. Right, so we can think as X goes to V transpose X, it's like you're doing V transpose. Then it goes to sigma V transpose X. It's like you're doing sigma to the result. Then it goes to U sigma V transpose X, which is AX. So it's like you're breaking up what A does into 3 separate steps. Okay, well, what is this? This is just a change of basis because V transpose is V inverse because V is an orthonormal matrix. So this is a change of basis to a basis of the columns of V or the rows of V transpose, which we were calling V1 through Vn. Right, that says take my vector x, which is written with respect to the standard basis, and write it with respect to this orthonormal basis V1 through Vn. You can also think of this as taking the standard basis of Rn and rotating it to the orthonormal basis consisting of vectors V1 through Vn. Okay, then what does sigma do, right? Okay, maybe I should also write where these vectors currently live, right? So this one is in Rn. V is just a change of basis from Rn to Rn. Now, when you multiply by sigma, it takes you to Rm because sigma is m by n. And then it ends up in Rm because U will also just be a change of basis. Right, so what does sigma do? Sigma scales the first R entries of the vector, right? So maybe I should introduce some notation. Let's call this, at this stage, let's say that this vector is y. This one is sigma y. And sigma has a really nice, easy to understand action on y. Right, y goes from y1 to yn. It spits out sigma 1 y1, sigma 2 y2, sigma r yr, and then sends everything else to 0. That's what that does. So you take x, you change to a nice basis, then in that basis, and of course this vector is also an Rm, what you do is you take the first R entries and you scale them by the singular values. Everything else becomes 0, and also you're changing the vector size potentially from Rn to Rm. So it's a sort of interesting thing, right? So this scales first R entries by the R singular values, and then the rest 0. That's just some shorthand way to say it. Now you have a vector in Rm, and what U does is U changes from the basis of vectors of U to the standard basis. So this is also some change of basis. It's a change of basis back, but remember, V and U are orthonormal matrices, which means that the bases that they represent are this, like, they look just like the standard basis, just rotated in some way. So you can think of what A is doing is it's taking the standard basis and it's rotating to some orthonormal basis. With respect to this basis, it does something really predictable. For the first R vectors, it scales them by the singular values, and it collapses the rest of the directions to 0. And then it takes you to Rm, right? That's what the sigma part does. And then you rotate from some basis to some other basis by multiplying by U. So it's just like diagonalization. It's a change of basis, an easy to understand transformation, and then another change of basis. But the easy to understand transformation is now from Rm to Rn, and it does something a little bit more complicated. Maybe it's not more complicated, just a little different than what what happens to an eigenvector under a square matrix. Okay, so this will summarize as a theorem. So let A equal U sigma B transpose in Rm by N be the SVD of A. So if we use the bases V1 through Vn of Rn and U1 through Um of Rm, then A behaves like the matrix sigma. Right, what this is saying is you can choose a nice basis of the domain and a nice basis of the codomain. That's really what these arrows are doing. These arrows are changing basis. You can choose a nice basis of the domain and the codomain such that the linear transformation A does something extremely predictable. Scales the first R basis vectors, sends everything else to 0. And remember, the rank of the matrix A is R. That means the range has dimension R. So what you're doing is like you're putting the basis vectors that don't get collapsed, you're putting them first. And all that's happening to them is they get scaled by A. All the other ones get collapsed because the range is only dimension R. It's a rank R matrix. So you put the first R, they're getting scaled, everything else goes to 0, and then the size of the domain and the codomain may not be the same. N might not be M. So this is really geometrically what the SVD is doing. It's rotating to a nice basis under which A has a nice action, and then it's rotating back. Again, going potentially between different dimensional vector spaces. But since it's rank R, we do know that what you'll end up with is an R-dimensional, the range will be an R-dimensional plane inside of Rm. Okay, so this is the start of geometry of the SVD, but now we'll talk about the geometry of the SVD in terms of the way that people actually talk about it, which is in terms of ellipses. Because these rotations that I'm talking about and these scalings, you can think about as rotations and scalings of an ellipse rather than just of the bases. And this gives you a nice way to actually see what's happening. So let me let me explain what I'm talking about. So geometry again. Geometry, let's say ellipses. Okay, so we know that if you have a linear transformation, it takes any m-dimensional plane. Let me write something down. If A from Rm to Rn, I guess I should say Rn to Rm, is a linear transformation, then we know that A takes any k-dimensional plane through the origin to a less than or equal to k-dimensional plane through the origin. Essentially, linear transformations take subspaces to subspaces. So if I have a line through the origin, if I map it under a linear transformation, it will either go to a line through the origin, or you could set everything to the 0 vector, so it could go to a 0-dimensional plane through the origin, depending on the properties of A, right? If A has a large kernel, then it could collapse dimensions down. If I have a 2-dimensional plane through the origin in Rn, and I map it under a linear transformation, you just look at where the basis vectors go. If they go to two linearly independent things, then you'll get a whole plane through the origin in the codomain. If it sends them to the same 1-dimensional space, then you'll get a line through the origin. And if it sends them both to 0, then you get a 0-dimensional plane through the origin. So we know that linear transformations do really nice things to k-dimensional planes. They get sent to other, potentially smaller dimensional planes in the codomain. It turns out that linear transformations, for very similar reasons, do very nice things to spheres and to ellipses. Okay, so let me define what a sphere is. So the sphere of radius 1, sometimes called the unit sphere, in Rn is just what you think it is. Let me explain the notation in a second. It's all the vectors such that their length is 1 in Rn. Okay, so this is called Sn minus 1 because the sphere is one lower dimension than the dimension of the space. So of course, we should think about R2 and R3 first, right? So I guess we could talk about in R1 first, actually. This is rarely used all that often. So R1 is just a line. S1 is all the vectors of length 1. So it's just 1 and -1. This is like a 0-dimensional sphere, right? Maybe I should color this, but let's use red. This is S0, and it's you rarely worry about S0. Okay. What is R2? In R2, you look at all the points, all the vectors of length 1, and you get the circle. The circle is a one-dimensional thing, right? It lives inside of R2. It's a one-dimensional sphere. This is what you would call S1. That's why we have an n-1 there. And in R3, again, it's all the vectors of length 1, so it really is now what most people would call a sphere. And again, the surface, it's just the surface, it's the shell, right? That's a two-dimensional thing, that's a surface. So that's why you'd call it S2, it's a two-dimensional sphere. I'm really bad at these math blackboard bold S's. It's not a letter that you often have to do in math. Okay, and we'll need something a bit more general than this because we also know about ellipses, at least in R2. And we'll need to know about hyperellipses, which are just like stretched out spheres, essentially, right? An ellipse is basically like a stretched out sphere, a stretched out circle in R2. So we also know that in R2, an ellipse has defining equation x1 squared over a plus x2 squared over b equals 1. Sorry, b squared, a squared. This is usually how it's given, right? As a quadratic when you're learning about it in, I don't know, algebra 2. These are, of course, positive numbers. And these things represent sort of like two different radii, right? Like a sphere has one radius, right? A radius, this one has length 1. But an ellipse can be longer than it is tall, right? And the point is that these numbers a and b control the length of these two what are called semi-axes, right? So a sphere is if I made both of those 1, then you would get a circle of radius 1. If I made both a and b 2, you'd get a circle of radius 2. But now you can control these things independently, right? And you can generalize this to Rn. You can look at the set of points. Sorry, it's still squared, but now I have n terms. And this will genuinely look like an egg in R3. So you take a sphere and you can like stretch it, and you have control over 3 different axes, right? So a sphere has one a sphere has one radius, but now this ellipse has three different directions that you could adjust its size, right? I could lengthen it this way. I could also like stretch it out this way, or I could stretch it out coming in and out of the page. So there's three different parameters that you can adjust. So in R3, the A1, A2, A3 will change what ellipse you're getting by changing the lengths of those semi-axes. Okay. Now the point is that what linear transformations will do to spheres is that they will send them to ellipses, hyperellipses. Did I use the word hyperellipse yet? This is called a hyperellipse. Hyper just because it's a higher dimensional analog of an ellipse. Okay, so why is this? The first point on this page was that you take k-dimensional planes to other planes, maybe of smaller dimension. And the way to see this is you just need to know what it does to a basis. So if you have a k-dimensional plane, you find a basis, has k vectors in it, and you just see where they go. And then A will take that entire plane, which is the span of those k vectors, to the span of the images. So some of them might go to linearly dependent things, in which case you would lower the dimension, but you're still going to go to the span of the images, and so you'll get some plane. So it's just determined by where it sends a basis of the plane you started with. For a sphere, it turns out that you just need to, like, if I just know what the linear transformation does to this vector and this vector, those two vectors determine your ellipse, which in this case is a circle. Now they can go to sort of any two vectors you want, and what you'll get is well, they may not any longer be the same length, so you could get an ellipse, and you could get an ellipse of potentially smaller dimension because I could send them to the same line, right? Potentially with different lengths. So what's going to happen is that we're going to send spheres to hyperellipses of less than or equal to dimension, which will eventually give us the following theorem. Actually, before I state the theorem, let me clarify something. So I said that this thing is called S1 because the circle is a one-dimensional thing. Okay, but for the purposes of this lecture, we're going to call this a two-dimensional ellipse because it has two parameters to it, right? The ellipse analog has two parameters to it. So we're going to call this this is S1, but we would call this a two-dimensional ellipse. Okay, similarly, the surface of a sphere, the surface itself is two-dimensional, that's why you call it S2. But again, really there's three parameters here, right? It's determined by three parameters. In other words, the unit ball is a three-dimensional thing. So we're going to call this thing a three-dimensional hyperellipse. And again, it can, of course, be egg-shaped instead. I just want to clarify this before I state the theorem because the theorem mentions r-dimensional ellipses. And by an r-dimensional ellipse, or r-dimensional hyperellipse, we mean the number of different axes it has. Okay, so here's the theorem. Okay, so let A be an M by N matrix of rank R. And let U sigma B transpose be the SVD of A. Then the following... Okay, also recall then R represents a linear transformation from Rn to Rm. Okay, then the following things are true. So 1, the image of Sn-1 under A is an r-dimensional hyperellipse in Rm. Okay, so we're starting in Rn, where we look at the the unit sphere in Rn, which I'm calling an n-dimensional hyperellipse because it lives in Rn, but topologically you would call it Sn minus 1, right? This gets mapped over under A to Rm. Where does it go? It turns out that it goes to like an ellipse because the lengths of the axes might change, and it's r-dimensional, so it could drop to a lower dimension, right? R is the rank of A. It can be at most, it's definitely not any bigger than n, so you can go to a smaller dimension. This is just like saying that any k-dimensional plane goes to a plane of dimension less than or equal to k. What I'm saying is the sphere goes to an r-dimensional hyperellipse in Rm. Okay, let's call this this hyperellipse is. We'll use this notation because it's the image of Sn minus 1 under A. 2, the lengths of the semi-axes. So these are like the parameters that determine what the ellipse is of this hyperellipse are the singular values of A. So now we're really seeing actually what the singular values are capturing. The singular values are capturing the parameters that determine the r-dimensional hyperellipse that the unit sphere gets sent to. Okay, 3. The first are left singular vectors. And remember, the first ones are in some sense the only ones that matter. u1 through ur are the unit vectors along the semi-axes of this hyperellipse in Rm. So the left singular vectors, in order, give you like the orientation of the ellipse, right? The ellipse has 3 semi-axes that are important, that determine like how egg-shaped or how round it is. The lengths of those axes are given by the sigmas, and the direction of those axes are given by the u's. And remember, the u's are orthonormal, right? So, and when you specify like the semi-axes of an ellipse, you're also specifying them in orthonormal directions, right? And 4, of course, the first are right singular vectors. V1 through Vr are the preimages in really Rn of the semi-axes. I guess really they'll end up being on the unit sphere of the semi-axes sigma 1 u1 sigma 2 u2 sigma r ur. Right? Again, the u's give you the direction of the semi-axes, but they're all length 1. The semi-axes have length sigma 1. So these are exactly the semi-axes of the ellipse, the hyperellipse A Sn minus 1. And the things that map to them under A, those are the right singular vectors, right? So in other words, AVI equals sigma I ui for all I between 1 and r. So it turns out that this is really what the SVD is doing, and oftentimes the way that you think about what the SVD is doing, you think about it in terms of sending spheres to some hyperellipse in terms of where it's sending the axes that define the hyperellipse, right? So Now we should understand why this is true. Again, this is given not in a really rigorous formal proof, but the point of this is to understand the geometry and the structure. Okay. So let's go back to this picture here. Not this picture. when did I... This picture here, right? Where what the singular value decomposition captures is rotation, then a nice linear transformation, then another rotation. We should think about what these things do to a sphere. If we know what they do to a sphere, then we can understand this theorem, because the theorem tells you what happens to a sphere under A. So what happens to a sphere under an orthonormal linear transformation, and then what happens to it under the sigma kind of linear transformation. And then once we understand that, we actually totally understand the theorem. Okay, so the first proposition is what happens if you have an orthonormal matrix. What does it do to a sphere? So if Q in R n by n is an orthonormal matrix, then the linear transformation represented by Q, right, the one from Rn to Rn, preserves dot products and hence preserves angles and lengths. Right, so this goes back to the fact that dot products know about angles and dot products know about lengths. So if you preserve the dot product, then it means that you preserve any angle, and it means you preserve any length. And so you can really think of an orthonormal matrix as some kind of rotation, because you're preserving all of the angles and all the lengths. Even in higher dimension, where it's not clear what a rotation means, what it means is that it preserves all rotations and preserves all angles and preserves all lengths. That's what I mean by it. That's what I'm thinking. Okay, and the point is that you can just prove this. So if V and W are vectors in Rn, then what is V transpose W? And what is QV transpose QW? Right? If I say that it preserves dot products, what I mean is after you apply Q, if you take the dot product, you get the same result as if you applied the dot product before you applied Q. Well, what is this thing? This thing is just V transpose Q, W. But Q transpose Q is the identity. So this is just V transpose W. Therefore, if you have an orthonormal matrix, it represents a linear transformation that preserves dot products. That means it preserves angles and lengths. Right? So if you have an orthonormal matrix, you send a sphere to a sphere, because the sphere is just defined as all the points of length 1 away from the origin. So if you apply an orthonormal matrix, you're not changing any of the points that have length 1. Right? So what an orthonormal matrix does to a sphere is it just rotates the sphere. Right? It's like you took the globe, although most globes only go on one axis, right? You took a beach ball and you just rotated the beach ball in space. Okay, so orthonormal matrices send the sphere to itself. Send a sphere to itself. Let me list this as a corollary. So if Q in Rn by n is orthonormal, then Q of the sphere is just the sphere. I'm not saying that every point on the sphere is fixed, right? What I'm saying is the whole sphere goes to the whole sphere, but there could be some rotation involved. Okay, and if B1 up through Bn is an orthonormal basis of Rn, then so is QB1 up to QBN. You probably can't see that, huh? And again, this is because if you preserve dot products, and you preserve angles and lengths. So if you have an orthonormal set of vectors, under an orthonormal linear transformation, it will stay an orthonormal set of vectors. Okay, now I've been calling these things rotations, and there's rightly a disclaimer in the notes that it only makes I'm only being technically correct if the determinant is 1, but the determinant of an orthonormal matrix could also be -1, in which case it's like it could involve some kind of reflection, right? And actually in higher dimensions it gets a little more confusing, but like in dimension 3 the plus or minus 1 just tells you whether the new basis you've chosen obeys the right hand rule, right? So I've been showing them with my right hand all the time. So I've only ever been modeling determinant 1 orthonormal things, but you could also have one where like you rotate and then I switch my thumb and index finger. That's also a legitimate orthonormal linear transformation. But again, I'm trying to give you the idea, right? I'm trying to give you how to think about it. So thinking about them as kind of like rotations, keeping in mind that it's not quite a rotation because the orientation between your axes could change, but it just takes one frame to another frame. Okay, it's a good point. And I'm glad it's here because I've been using the word a little bit loosely, sort of. Okay, but it also says, for the purposes of intuition, you should think about it as a rotation. I do think about these as rotations when I just try to understand the intuition for what's happening. Okay, so I just checked the time, and we are very close to the end of the allotted time. So I'll stop here for today, and next time we'll finish up. I mean, we're literally just a hop, skip, and a jump away from understanding this theorem fully. In fact, I bet you could figure out before next lecture. But I'll finish up this theorem next lecture, and then we'll start getting into at least 2 lectures worth of applications of singular value decomposition. This might be the most useful contribution of linear algebra to the world so far. All right, see you then.